Welcome to ELEC142 Semester 2 Problem Sheet 5. In this power question sheet we're looking at information about power. So let's have a look too close at question 1. Good place to begin. So in this question you'll say 1. The voltage across a component is measured at 3 volts RMS and the current through it is 50 milliamps RMS. The current leads the voltage by 10 degrees. Using this information, calculate first of all the power factor, second the active power, 3 the reactive power, and 4 the apparent power. And then part B, we're going to draw the power triangle for the circuit using the values that we've just calculated. And then part C asks us, is this component in the circuit likely to be an inductor or a capacitor, and give an explanation. So let's work out how to tackle this. So let's start with this one. So I've redrawn my little circuit here. We can see that I've just written very quickly all the information that I've been given to help me solve this. So here's my mystery component. I've just drawn a block and put a question mark on it. What we do know is that coming into this component we have 50 milliamps RMS, and across it we have a voltage of 3 volts RMS. And this is our secondary information over here, is that the current leads the voltage by 10 degrees. So this is using all of the information you have in this slide. So I'd recommend you become very, very familiar with this slide because it contains all this really useful information. And if you've got a couple of these values, you can work out everything else. So this triangle really helps solve things. So P is the real power. So this is in watts. This is the energy that your device is consuming. That's what's useful to know. So that's going in the real direction along here. Q is an imaginary value. It's the reactive power. So this is sometimes called the imaginary power, as I've said. So this also tells you a couple of different terms you'll find. So the real power is also sometimes called the active power, and the reactive power is also sometimes called the imaginary power. An important point to note is that Q is going to be in the positive, wrong slide, it's going to be in the positive direction for inductors and in the negative direction for capacitors, because if you think about what happens when you calculate the impedance, it's positive J for inductors and minus J for capacitors. So this is where we get this change of direction. It doesn't affect P, it's in the real direction, it affects Q. Then it will also affect S, which is the apparent power. So it's worth getting to grips with this triangle. It's also worth noting, and I said in the lecture, but I haven't been able to show on the PowerPoint slide, is that this angle here is theta I minus theta V. So that's the power factor angle. The power factor is cosine theta I minus theta V. The power factor angle is just theta I minus theta V. So there we go, and you'll see the power factor in textbooks sometimes written as theta V minus theta I. It's just from a different way of deriving it, which I went through in lectures. But this triangle is very useful and it helps you not get confused between what these quantities are. This also ties into the beer analogy, if that's helpful for you. And I've just put the units here as well, just to sort of confirm it. But anyway, it's this power triangle that's really important, and these equations that we're going to be using to solve a lot of the problems on this question sheet. So let's go back, and we're going to find, first up, the power factor. Well, the power factor is the cosine of theta I minus theta V. We're told that I leads V by 10 degrees, so we know that this is going to be 10 minus 0. That's fine. So we need to find what the cosine of 10 is, and if you put that in your calculator, make sure your calculator is in degrees. The power factor should always be a value between 0 and 1. If it's not between 0 and 1, you've done something wrong. Please check your calculator mode, because that's the most common problem that people have. So our power factor is 0.985. So far, so good. Next up, we're asked to find the active power, and as we saw on this slide, the active power is also the real power, so we need to find VRMS times IRMS multiplied by the power factor, which we've actually just worked out handily enough. So let's just put the values in. So we were given VRMS in the question, which was 3, and IRMS also in the question, which was 50 milliamps. So that's 50 times 10 to the minus 3. Then we need to multiply it by the power factor we've just worked out, which gives us an active power of 0.15 watts. Please remember your units. You'll lose marks if you forget to include them. So that's one side of the power triangle we found. Next up, we're going to find the reactive power, or Q. So this is the imaginary power, and we use our formula. So S is equal to the RMS voltage times the RMS current. Sorry, no, we're going to do Q, not S. Q is the RMS voltage times the RMS current times the sine of the power factor angle. Okay, so it's slightly different this time because we're finding the opposite rather than the adjacent angle, the adjacent side. So what we've done is we knew that this was 10 degrees, this angle, so that's what I've done there. It's sine of 10 degrees. So it's 3 times 50 milliamps times the sine of 10 degrees, which will give you an answer of 0.026 vars. That's good. Right, final side of the power triangle we're going to find. We're going to find the apparent power, which is S, and this is kind of the easiest one. It's just VRMS times IRMS. So it's this one in the middle, it's S. It's the longer side of the triangle we're interested in now, the hypotenuse. So just put the values in. 3 times 50 times 10 to the minus 3 gives you an answer of 0.15 volt amperes, or VA. So that's all of those bits done. That's part A done. Next up, part B, you are asked to draw the power triangle for this circuit using the values we've just worked out. So let's do that. So this is just a case of just sketching that triangle, labelling the sides. If you can, please try and give it a little bit of scale. So Q is small compared to P, so don't do it so Q is absolutely massive. It gives you a bit of indication of scale, and I've also actually marked the power factor angle on here as 10 degrees. You don't have to draw that, you just ask for the sides, but it helps to work things out. So that was part B. It's just a question of drawing and giving a bit of context. If you find it helpful to solving these questions, there's nothing to stop you sketching this triangle with those sides before you work these out and then drawing it to scale a bit further down. That's also absolutely fine. It's up to you if you want to do the maths first or if you want to do a bit of sketching first. So that leads us on to question C. This is a little bit of a question you might not be used to answering. So this isn't just asking you to plug some numbers in and get an answer out. This is asking you to actually think about what's going on. So it's a mystery component. We've worked out some answers. Now we want to make a deduction using what we know. Is this mystery component, assuming it's just one component, likely to be an inductor or a capacitor, and give a reason? So I've just said, when I was introducing this, is that Q is going to be positive for an inductor and minus for a capacitor. So the power triangle would be a mirror image about P if it was a capacitor. So that really gives us our clue. So because Q is positive, we know that it's an inductor. It's most likely to be. So that's what I've done. So the mystery component is most likely to be an inductor. We can tell this because the reactive power Q is positive. For a capacitor, this would be negative. There's another way you can do that as well, is you can think about it, instead of thinking about the value of Q, you can think about this power factor angle instead, because this would be negative if it was a capacitor. That's the other reason you could give. So because we can see that theta I minus theta V is positive. For a capacitor, this would be negative. So either of those two answers would be perfectly acceptable. So that's question 1. So this is question 2. This time we're looking at instantaneous power. So you're told an instantaneous current I of t is equal to 250 cos omega t in milliamps, flows through a resistor which produces an instantaneous voltage, V of t is equal to 5 cos omega t volts. Write an expression for the instantaneous power, P R of t. So this is the instantaneous power which is consumed by a resistor. So how do we go about solving this one? Well, this is really actually a very quick question. It's not as terrifying as you'd think by the sound of it. So it's just a resistor that we have. It's connected to a source. We're not really told any other information. We just know that I of t is 250 cos omega t milliamps and V of t is 5 cos omega t in volts. When you're doing instantaneous power, all you need to know is that it's the instantaneous current times the instantaneous voltage. So that's what you've done here. So I've written the expressions down here: 250 cos omega t milliamps times 5 cos omega t volts. Because the magnitude affects the magnitude, the units affect the magnitude, I've moved the milliamps over to here. So it's actually 250 times 10 to the minus 3 milliamps, so that's what it is there, times 5, that's the part from the voltage. So what I've done is I've just moved all of the magnitude information over to this side. And then we're just left with two cosines multiplied together, and they're the same. It's cos omega t times cos omega t, which gives us cos squared omega t, and that actually gives us a value in watts. So our final answer is multiply the magnitudes together gives us 1.25, and then it's cosine squared omega t in watts. So that's your final answer there. So hopefully that shouldn't have taken you too long to work out, because we're not asked to work out the values at a particular point of time. You're just writing an expression. As you'll see in the next question, we're going to go into this in a little bit more detail.